And let's get into Pytrees, or let's get further into Pytrees. I think we already went through this whole thing, no? Let's see. First of all, let's open a new notebook. Pytrees we already did. Let's do instead a new one. New notebook. I don't know if we went through this full thing, but anyway, let's move on. Getting into pseudo-random numbers. Let's do that. And this, alright, if all scientific papers whose results are in doubt because of bad rands were to disappear from library shelves, be a gap on each shelf about as big as your fist. Interesting. In this section we focus on Jax.random and pseudo-random number generation. That is the process of algorithmically generating sequences of numbers whose properties approximate the properties of sequences of random numbers sampled from an appropriate distribution. P, R, and G generated sequences are not truly random because they are actually determined by their initial value, which is typically referred to as the seed. And each step of random sampling is a deterministic function of some state that is carried over from a sample to the next. Pseudo-random number generation is an essential component of any machine learning or scientific computing framework. Generally, Jax strives to be compatible with NumPy. Pseudo-random number generation is a notable exception. Better understand the difference between the approaches taken by Jax and NumPy when it comes to random number generation. We'll discuss both approaches in this section. Random numbers in NumPy. Pseudo-random number generation is natively supported in NumPy by the NumPy.random module. In NumPy, pseudo-random number generation is based on the global states, which can be set to a deterministic initial value using NumPy.random seed. So let's do this. NumPy seed. Repeated calls to NumPy's stateful pseudo-random number generators mutate the global state and give a stream of pseudo-random numbers. Cool. So we got 3 different random numbers. Oh! Notice how these random numbers are the exact same as these. Interesting. Underneath the hood, NumPy uses the Mersenne twister PNRG to power its pseudo-random functions. The pseudo-random number generator has a period of that, and at any point it can be described by 624 32-bit unsigned integers and a position indicating how much of this entropy has been used up. You can inspect the content of the state using the following command. Let's see. Define print truncated random state. To avoid spamming the outputs, print only part of the state. Full random state is that. Print full random state. Truncated random state. Okay. State is updated by each call to a random function. So if we do that again, interesting how there's 0 and 1 here. Okay. And these are all slightly different. Underscores NP random not uniform. Print truncated random state. I don't know how this is different though. NumPy allows you to sample both individual numbers or entire vectors of numbers in a single function call. For instance, you may sample a vector of 3 scalars for a uniform distribution by doing this. So add new random seed and then uniform. So that's 3. Okay. NumPy provides a sequential equivalent guarantee, meaning that sampling n numbers in a row individually or sampling a vector of n numbers results in the same pseudo-random sequences. np.randomc0 print individually, np.stack, np.random uniform for blank and range, np-seed all at once. Interesting. And this is the undesirable thing for running on accelerators. It's because it's not really random. Air numbers in Jax. Jax is random. Wait, let me move this over first. What happens if we do this? Random seed 1. Whoa. It's a lot different. But a random seed 2. It's not so much different. A random seed 3. Oh, okay. Numbers in Jax. Jax's random number generation differs from NumPy's in important ways because NumPy's PRNG design makes it hard to simultaneously guarantee a number of desired properties. Specifically, in Jax, we want PRNG generation to be reproducible, parallelizable, vectorizable. Should that be a Z? So it seems like it is reproducible based on what we were seeing here. Parallelizable, I don't know about that. Vectorizable, I don't know about that. We will discuss why in the following. First, we will focus on the implications of a PRNG design based on a global state. Probably faster just to say pseudo-random number generator. Maybe not. Consider this code. So we got import NumPy, got a random seed, bar, so random uniform, baz. Find foo. So return bar plus 2 times baz. Okay. Cool. Just adding some random numbers. The function foo sums 2 scalars sampled from a uniform distribution. The output of this code can only satisfy requirement number 1 if we assume a predictable order of execution of bar and baz. This is not a problem in NumPy, which always evaluates code in the order defined by the Python interpreter. In Jax, however, this is more problematic. For efficient execution, we want the JIT compiler to be free to reorder, elide, and fuse various operations in the function we define. Yeah. Okay. There's JIT compiler. It changes everything. So it seems like, yeah, so compiling means that you get a little bit of, you take the damage of a little bit of extra time to like do all this rearranging and stuff, but it runs faster than the accelerator. There's a net positive when running super long stuff. Further, when executing in multi-device environments, execution efficiency would be hampered by the need for each process to synchronize a global state. Let me fix this lighting. I feel like it's a little bit too bright. Maybe this is too bright as well. Let's try just this for now. Sure. Okay. If you assume the predictable order of execution for bar and baz, okay, boom, boom. So requirement number 1 is reproducibility. Okay. Okay, yeah. Also, you need a global state to synchronize. Explicit random state. To avoid the issues, Jax avoids implicit global random state that tracks state explicitly via random key. From Jax, import random. Get key equals random key 42 per key. Okay. Why did that take so long? This section uses the new style types PRNG keys produced by random key rather than the old style raw PRNG produced by. Okay. A key is an array with a special data type corresponding to the particular PRNG implementation being used. In the default implementation, each key is backed by a pair of uint32 values. key is effectively a stand-in for NumPy's hidden state object, but we pass it explicitly to Jax random functions. Importantly, random functions consume the key but do not modify it. Feeding the same key object to a random function will always result in the same sample being generated. Yeah, okay. Let's do this. And then let's do from NumPy import random and do this. How would this work in NumPy? If I say NumPy random seed equals 0, and then you want to print, oh whoops, so probably instead of normal would be like uniform, or is there some NP normal thing? Oh, maybe not. Let's just do this. So they're different numbers, but same as above there. I don't know if what we're doing is equivalent. We'll leave it in there for now. Alright. Reusing the same key, even with different random APIs, can result in correlated outputs, which is generally undesirable. The rule of thumb is never reuse keys unless you want identical outputs. Using the same state will cause sadness and monotony, depriving the end user of life-giving chaos. Nice, okay. I wonder who wrote that. Jax uses a modern 3-fry counter-based PRNG that's splittable. That is, its design allows us to fork the PRNG state into new PRNGs for use with parallel stochastic generation. In order to generate different and independent samples, you must split the keys explicitly before passing to a random function. I feel like we saw a lot of this in the very first tutorial. For I in range 3, new key, sub key equals random split. Del key, the old key is consumed by split. We must never use it again. Okay. Value equals random dot normal sub key, delete sub key. So it seems like every single time you use a key, you want to delete it. Control. Alright, cool. Let's do it. Uh-oh. It's because we need to do this again. Cool. Calling del here is not required. We do so to emphasize that the key should not be reused once consumed. I'm a little curious here of like why this is the exact same output as they got, you know? If it's really like random number generation, we would think it shouldn't be the same. Thing is, I'm wondering why you want random number generation to be reproducible. That seems kind of counterintuitive to it being random. It shouldn't be predictable or repeatable. So what are we doing here? So we're splitting key. So key was already made up here. Random key 42, so I mean it's all based on the seed then, I guess. Yeah. Okay. Calling del here is not required, but we do so to emphasize that the key should not be reused once consumed. Alright, so it automatically does that, but I was curious about that. Alright, Jax random.split. The random.split is a deterministic function that converts one key into several independent in the pseudo-randomness sense keys. Okay. We keep one of the outputs as the new key and can safely use the unique extra key called subkey as input into a random function and then discard it forever. If you wanted to get another sample from the normal distribution, you would split key again, and so on. The crucial point is that you never use the same key twice. It doesn't matter which part of the output split key we call key and which we call subkey. They're independent keys of equal status. The key subkey naming convention is a typical usage pattern that helps track how keys are consumed. Subkeys are just destined for immediate consumption by random functions, while the keys retain to generate more randomness later. Gotcha. So the above example will be written precisely as this. Which discards the old key automatically. It's worth noting that, wait, let's look at this. So it's written basically exactly the same way, except you're just not saying del. Which discards the old key. It's worth noting that splits can create as many keys as you need, not just two. Whoa. How do we print them all out? Probably just print for key in, can I say, what is 42 subkeys? I don't know what that notation is with the asterisks. 42 subkeys. I have to say range of length. Can I say type? It's a list. Okay, in that case, I can do this. Print key for, wait, for I in range of length of 42 subkeys. Oh, whoops. And then print key. Is that gonna work? It's not gonna print something weird. Yeah, it is printing something weird, but whatever. But they're all the same though. Isn't that bad? I would assume that you wanted these to each be different. 42 unique subkeys. Oh. That's probably like a dimension or something. So what I really want to see is how did they... So I basically want to do this exact same thing. So I want to print 42 subkeys key, then I say random dot normal key. Yeah, no, I don't get it, I guess. Figure that out later. Like a sequential equivalence. Another difference between NumPy's and Jax's random modules relates to the sequential equivalence guarantee mentioned above. As a NumPy, Jax's random module also allows sampling of vectors of numbers. However, Jax does not provide a sequential equivalence guarantee, as doing so would interfere with the vectorization on single instruction multi. What is the D stand for again? Simmed architecture tool data. In the example below, sampling 3 values out of a normal distribution individually using 3 subkeys gives a different result to giving a single key. I might want to go in the Jax documentation and change that. Single key and specifying shape 3. Key equals random key 42, subkeys is random split key 3, sequence equals NP stack. Usually so since we're basically at the end here, and we've been going on 20 minutes, it's past my bedtime, I'm going to stop here. I also want to remember to go in and change this, so I want to leave the page here. Hopefully I'll start rereading, and I'll see this again. And then I will submit a pull request on the GitHub for the documentation. Anyway, that was pseudo-random numbers in Jax. Next time we'll do this. We'll probably spend a lot of time just setting up my GitHub in order to be able to edit to submit a pull request on the Jax repository. And then after that, if we have time, we may get into distributed arrays and automatic parallelization, or you might go back to how to scale your model. I've been reading all about TPUs on my own, so we will probably skip the boring part where I just read to y'all and get right into the problems. Let's see, what's the first one? Say you want to sample from a 200 billion parameter model and BF16 that's split across 32 TPU V. For P, how long would it take to load all the parameters from HBM into the systolic array? Numbers above. Okay. Well, anyway, that's it. That's all, folks. I'm logging off. Good night, everyone.